Mercury appears to have a solid silicate crust and mantle overlying a solid iron sulfide outer core layer, a deeper liquid core layer, and a solid inner core. The planet's density is the second highest in the Solar System at 427 grams per cc, only slightly less than Earth's density of 515 grams per cc. If the effect of gravitational compression were to be factored out from both planets, the materials of which Mercury is made would be denser than those of Earth. With an uncompressed density of 3 grams per cc versus Earth's 4 grams per cc, Mercury's density can be used to infer details of its inner structure. Although Earth's high density results appreciably from gravitational compression, particularly at the core, Mercury is much smaller and its inner regions are not as compressed. Therefore, for it to have such a high density, its core must be large and rich in iron. The radius of Mercury's core is estimated to be 2020 plus or minus 30 kilometers, 1255 plus or minus 19 miles, based on interior models constrained to be consistent with the value of the moment of inertia factor given in the info box. Hence, Mercury's core occupies about 57% of its volume. For Earth this proportion is 17%. Research published in 2007 suggests that Mercury has a molten core. Surrounding the core is a 500 to 700 kilometers, 310 to 430 miles, mantle consisting of silicates, based on data from the Mariner 10 and Messenger missions. In addition to Earth-based observation, Mercury's crust is estimated to be 35 kilometers, 22 miles, thick. However, this model may be an overestimate and the crust could be 26 plus or minus 11 kilometers, 2 plus or minus 8 miles, thick based on an airy isostasy model. One distinctive feature of Mercury's surface is the presence of numerous narrow ridges, extending up to several hundred kilometers in length. It is thought that these were formed as Mercury's core and mantle cooled and contracted at a time when the crust had already solidified. Mercury's core has a higher iron content than that of any other major planet in the Solar System, and several theories have been proposed to explain this. The most widely accepted theory is that Mercury originally had a metal-silicate ratio similar to common chondrite meteorites, thought to be typical of the Solar System's rocky matter, and a mass approximately 25 times its current mass. Early in the Solar System's history, Mercury may have been struck by a planetesimal of approximately 1/6 Mercury's mass and several thousand kilometers across. The impact would have stripped away much of the original crust and mantle, leaving the core behind as a relatively major component. A similar process, known as the giant impact hypothesis, has been proposed to explain the formation of the Moon. Alternatively, Mercury may have formed from the solar nebula before the Sun's energy output had stabilized. It would initially have had twice its present mass, but as the protosun contracted, temperatures near Mercury could have been between 2,500 and 3,500 K and possibly even as high as 10,000 K. Much of Mercury's surface rock could have been vaporized at such temperatures, forming an atmosphere of rock vapor that could have been carried away by the solar wind. A third hypothesis proposes that the solar nebula caused drag on the particles from which Mercury was accreting, which meant that lighter particles were lost from the accreting material and not gathered by Mercury. Each hypothesis predicts a different surface composition, and 2 space missions have been tasked with making observations of this composition. The first Messenger, which ended in 2015, found higher than expected potassium and sulfur levels on the surface, suggesting that the giant impact hypothesis and vaporization of the crust and mantle did not occur, because said potassium and sulfur would have been driven off by the extreme heat of these events. BepiColombo, which will arrive at Mercury in 2025, will make observations to test these hypotheses. The findings so far would seem to favor the third hypothesis. However, further analysis of the data is needed.